Okay, so let's see a little of purity in languages. Haskell was created following the Miranda language. It was one of the dozens of functional languages that appeared in 1987, I think. But Miranda was proprietary software, so the community wants to create a language that was open source. Um, so what it was designed for teaching, research, and today uh, it's a language, the most used language for academic purpose. And the language is part of the ML language, like OCaml and standard ML. And its semantic was heavily inspired by Miranda, but also Hope, that it's another functional language that I will not talk about. So let's go. I have an image to show the Haskell features. So it has memory safety, garbage collection, native code, stacked types, rich types, purity, laziness, concurrence, metaprogramming, and the ecosystem is kind of huge. But I will only show 4 of these features. And the first one is the type-driven development. So Haskell is a strongly stacked typed language based on the Hindley-Milner type inference. Um, it's a type system for Lambda calculus for supporting polymorphism, parametric polymorphisms. The Hindley-Milner type algorithm allows the program to code features based on types of values. So you don't need to declare the types. The compiler will also already know the types. Also, with Haskell polymorphic variants, these features we can build expressive and declarative programs. So a tiny example is the definition of the lambda calculus syntax. So here we're creating a variant, a polymorphic variant, and lambda calculus have 3 constructors: a variable, so we create the variant var to handle a string. The second constructor is the application, the function application, that receives expression and applies the first expression to the second. And the last constructor is the lambda that receives a variable and expression. So we can build a parser, for example, and an interpreter from lambda calculus based only with this definition of the syntax. Another cool feature is pattern matching. So history, we can define pattern matching as a mix of features like string matching coming from Snowball language, but today pattern matching is used to match not only values of the entities, but also the structure of this entity. My example, I'm pattern matching in a list of 1 to 10. In the first case, I matched a list with at least one element. The second case, at least 2 elements and the tail of the list. And the general case for any other kind of lists. We also can use pattern matching in function definitions. So I don't know, if we define a function map, we can map in a list and get the tail, the head, the head and the tail, and then the function body. Personally, my favorite feature is type classes, which is a type system construct that support ad hoc polymorphisms that let you to create operators overloading and functions to be applied to different types without changing the function by itself. So here's an example. We define a type class, Proofy. So before I explained it, Haskell only have um, two Boolean values, let's say false and true. On these, any other value don't returns of the bool class. But I can create a new type class, trophy, that needs to implement the check function and receives an argument of type A, which is any type, and returns bool. So I will implement the truth type classes to a list where if check receives an empty list, it's false, and any other list is true. I also implemented the truth type classes to the maybe monad. I will explain the maybe and either and monads in a second. But if you receive nothing as an argument, it's false, and just or some, it's true. And also the monad either, where if we receive pattern matching on a left structure, we returns false, and on right structure returns true. So the major feature of Haskell is purity. It's your purity and lazy evaluation. The majority of languages performs structured evaluation. So when you call a function with arguments, their arguments are evaluated before passing to the function. However, Haskell prefers the lazy evaluation. That means that this value will only be evaluated when requested. So if you don't use the value in your code explicitly, they won't be computed. Also, for the purity feature, we have one problem. Haskell is a pure functional language, it avoids side effects. And what is a side effect? Let me code a function that modify a global value. For example, it is an impure function. When we have a function with that prints something in the screen, it's a side effect. So if Haskell avoids side effects, how we can interact with the real world? Haskell encapsulates these side effects in the so-called monads. I will not explain exactly what monads is because it's a mathematical property, but in Haskell, it encapsulates the state in a such way that don't overload the function scope. So you can't perform an I/O action, the I/O monad, or in other words, you can print to the screen in a function that only returns int, for example. So we have some examples. First, to show business. So we have a let expression that allow us to create some variables, and we created the variable a, b, and c. But in the body of the let expression, we only use a and c. So b will never be computed. This laziness allows us to manage infinite structures too. So we can take 4 elements of an infinite list. So that's so cool. And for the feature, the period field, I'm using the function putStyle ln that prints the given string to the screen and returns IO, the IO monad. So it performs IO action, and that's it. You can return in. I can't create a function. I don't know. X and some that receives A and B, and then the test strln that will never compile first because it don't test the type, so you are trying to sum numbers and then trying to pass to a function that receives the string. But also, if you try to return this function, the stack trace will only return the IO monad. So you encapsulated the state. So for another monad example, we have the type result, or either. It has both these names, and it receives two types as arguments. And the first constructor is a failure or left that represents an error on your application and receives the type A. And the right side, or the success type, receives the second type B. And also the monad option, that, or it can be called maybe, that return none or nothing, or some, or just, that represents a value. And that are the features. So let's go to the live coding. We create a module. Each file in Haskell is a module, so the file name is the module name. So we can try to implement the Boolean algebra in Lambda calculus with Haskell. So as Haskell is a Turing-complete language, and Lambda calculus and Turing machines are the same, so we can make an inception here. So firstly, we will hide the standard library functions to not have conflicts. We have the not and the or. And to start simply, we will implement the true function. The true function receives two arguments and it returns only the first one. So simple. The false is the opposite. It receives two arguments and ignores the first. Okay, now we have the true and the false functions. We can implement the not function. So the not function will reserve true or false, and then will return the opposite of this function. So if it receives true, it returns false, and if it receives false, it returns true. It receives bool, and applies this bool function to the false and true. So if it receives true, it will return false, and if it receives false, it returns true. Now the end function. So it reserves two bools. So A and B, and then applies A to B where false, and false, sorry. I will execute this code so it will be better to see in action. And the OR function that also receives A and B, and and applies A, true, and B. To finish, we can implement if then else. It receives a given value, V, the truth branch and the false branch, and applies the V to the truth and false. Okay, so let's try to execute this. So we can execute true, and it returns always the first one, and execute false, and we return the second one. And another cool feature of Haskell is that all functions are oh my god, I forgot the word, tiered by default. So we can apply one true to true one with only one argument. And if you try to see the type of the one true, it will be returning that receives one argument. Let's ignore this type class, and we will return one argument and return the first one. So if we apply one true to any other value, we only return the one. Also, this function inferred that it is per turn is about to receive only the non-type classes. So if try to apply to a string, we can ignore this, and the type will not raise an exception. Okay, true and false. Now let's try to test not. So if not returns true, oops, let's print. I'm not sure if it will work, but okay, no. So to print something in the screen, it needs to be part of the show type classes. So I didn't implement the show instance of any function here. So let's try to create a var result. So not true result. True. Wow. Bool false true. Oh yes. So the result function will act like the false. Yes. But it's kind of confusing. So
what about not true?
So we can apply here not true. We can apply this to the result. So yes, or true false. So it's true, and then the first one is returned.
Why do you need the $sign?
So the $sign is a function applicative operator or function that applies the result of this expression, the next expression, to the function in the left.
But what would it happen if there was no $sign?
It is kind of the compiler will not how to evaluate this expression. So, well, we don't know because this is a composition, so we can make this too. No. Yes, it's kind of different. It's not and then true. The composition is kind of magical, so I can use parentheses too. If you try to do that, you also do. Okay, we're done with parentheses. But yeah. So let's try to use it to the end. I don't know if the component will probably yes. Okay. Okay. And false. Yes. Oh. There. And the or. So we have true. True. And false. Yes. And finish the if then else. So if true, then 1, then else 2. And if false, okay. And if try to apply not false, so yes, correct. And true, false. Okay. Oh, yes, that's correct. And that's it.
Okay, thank you very much. I have a few questions, but first I want to ask Lucas, Bruno, Sam, have any questions?
No, I think I'm good.
Oh, okay, maybe later. Sam, okay.
I have a slightly odd question. What are you using to do your presentation?
Oh, Emacs.
Emacs. Okay.
And the org3 presentation library.
Cool. Thank you.
Sorry, what's the name of the library?
org3 presentation.
How do you spell that?
Oh, ORG 3 the
Oh, okay.
TREE and presentation.
ORG 3
presentation. Sorry, slide org3 slide.
org3 slide. Maybe
Yeah. It's because the Emacs comes with the org mode that is a markup language like Markdown. Yeah, Bruno sent the link.
Yes, it's actually 3, like 3, the plant, not
yes,
the vegetable, not a number 3. Okay, so that's it was also one of my questions. I liked one point that you said that no, this is actually related to Pietro's talk before, because Haskell was created because it's from your talk, because you said, oh, Miranda was great, but it was closed source, so they created Haskell so that it would be open source. So my question, because I know that now Miranda is open source.
Yes.
So maybe if at that time, if at that time the guy that created Miranda said, "Oh no, it's free, it's open source," maybe there would be no Haskell. Is that what you mean?
No, I don't think so, because Haskell, for example, was the first language to implement type classes, and then standard ML implemented. So probably would become in another time, but we come.
And the next question, it's more provocative. If Haskell is so great, why isn't it the #1 language in the world?
It's the best question. So the Haskell ecosystem, and specifically the build programs, the build system, it's kind of confusing and scary some beginners. So we have Cabal, that was the first build system implemented, but a lot of libraries breaks, and then they created Stack, that's another build system that also breaks. So we have some problems to developing Haskell, but also some people say that the type system is scarce, but I think that is a type system, and it's more like the compiler errors, because the compiler error is kind of strange. Like if you try to apply the true, we'll print this error message, and okay, we don't know what to do about what is show, what P10, P20, and so on. But see, I didn't type annotate any function here, so the type system in itself, it can be complex, but you don't need to use this complexity anytime. So if you try to see the type of end function simple, it is this scary thing, but I don't need to annotate that. The compiler will know. Also, the third explanation that why Haskell isn't not so used, it's because we can't do some practical exercises with Haskell in simplicity. So I'm trying to implement some Boolean algebra, but I don't know, for implement a web server, for example, it's kind of difficult because of the ecosystem. We have frameworks like Servant that is type safety web server, but it's kind of difficult to get used to the framework.
Yes, maybe that's just the focus, it seems, for me, from kind of outside, it's that Haskell is more focused on research.
Yes.
If you want to teach functional programming, people, even from the Haskell community, recommend Racket.
Yes,
Maybe.
because we can do practical things with Haskell. So imagine if we need to teach each student to install the Haskell compiler, and then the build system, and then so it's a lot of work. But those features, the language features, it like, I don't see these features in any other language. Like, okay, exist, but in a such way that with this expressiveness and this declarative way, I don't see. So we can create an infinite structure, and then we will be computing these forever. So it's so different.
Okay, thank you very much, Luis, Bruno, Pietro. Any other question? Sam?
No.
If you don't have any question, I'm going to... Oh, yes? No? If you don't have any question, I'm going just to stop the recording.